So back in chapter 6, right, we were going over Walsh diagrams, and we were able to use Walsh diagrams, which were correlation diagrams between MO diagrams of different symmetry, to predict structure, right? That's a great goal for us, great goal for chemists. And so what we want to be able to do is a similar thing for transition metal complexes. For a given electron configuration, we want to determine which electron structure is favored amongst various geometries and various coordination numbers. So you've got a metal and you've got a bunch of carbon monoxide around, right? How many carbon monoxides are going to bind and in what geometry? That would be a valid type of question, right? And so one way to do this is to derive MO diagrams for all the different trial structures and compare energies. Try to make Walsh diagrams where you can to make your life easier. There's a lot of permutations and it's still going to get quite complicated. So what we're going to do is something that's a little bit easier. It's called ligand field theory. And so ligand field theory starts as a starting point, starts with spectrochemical series. Okay, we've gone over the spectrochemical series. We said that crystal theory can't predict this trend because it's based only on electrostatics, but that ligands like carbon monoxide and cyanide are strong field ligands. And ligands like iodide and bromide are weak field ligands, giving rise to very narrow delta O splitting, or delta T if you're in tetrahedral. What ligand field theory does is it uses fudge factors essentially. So these are tweaking the numbers, okay, that consider the sigma donating and pi donating or accepting characters of the ligands to then go ahead and predict sort of the overall structure of the molecule. And we are going to be using a subset of ligand field theory called the angular overlap method, or AOM. So this is the idea of the angular overlap method. And this is now zooming into a portion of that molecular orbital theory diagram that we derived. Consider if you have a sigma donating ligand. You have some orbital, let's say this dz squared. And if it's sigma donating, this is going to go up in energy by the amount, some amount, right? Versus where it was. Where does that come from? That comes from this MO diagram right here. We're talking about this sigma star antibonding, okay? So here's the original starting energy of the d orbital, and it rises up in energy. This is an antibonding orbital. So if you have more of a bonding interaction, since this is becoming an antibonding molecular orbital, it's an atomic orbital over here, but now it's over here, it's a molecular orbital, it's antibonding. The more sigma interaction you have on the ligand, the higher this is going to get raised, right? So we're going to call the value that this gets raised above where it was when it's an atomic orbital, E sigma. And then we know that the ligand molecular orbital is going to go down, right? And what is that? That is, starting from the salt, right, sigma salt, and going down, okay? Because it's a bonding interaction. And that's less relevant to us most of the time, but it's going to go down. It's going to go down some value. It's going to go down less than whatever the value of E sigma is. Why does it go down less? Remember, antibonding orbitals are always raised higher than bonding orbitals are lowered, right? Okay. So this is the antibonding orbital relevant to crystal field theory. This is the bonding orbital that we only see in the MO diagram, okay? E sigma is the value of E sigma is gonna vary depending upon the extent of sigma bonding. It's always gonna be positive. So if you have a strong sigma bonding ligand, makes strong sigma bonds, E sigma is gonna be very large. This is gonna go very high. This is gonna go very low. If you have a weak sigma bonding ligand, these values aren't gonna change that much. So the whole idea here is that as your interaction angle changes, the amount of overlap is going to change, and that's going to change the magnitude of E sigma. So, if you have direct, this is your ligand, this is your metal, in this case, in this orientation, you have very good overlap, and so that's going to give a high value of E sigma. Here you sort of have side-on interactions, so that's going to give, bonding through the donut here of dz squared, that's going to give you less overlap. Here you have the p orbital, the ligand of a p orbital, at a different angle, and it's actually in a node. And so that's going to give no overlap, all right? And so the degree of overlap is in part what determines the magnitude of E sigma. Okay, E pi is very similar, except now you need to have two sets of lobes overlapping, right? So as shown here, right, you have this side-on interaction. We have two lobes of the p orbital and two lobes of the d orbital interacting. That's what we call E pi. E pi is going to be greater than 0 for donor ligands, but for accepting ligands, it's going to be negative. Okay, and the magnitude of E pi is always going to be less than the magnitude of E sigma, because pi bonds, we know, are always weaker than sigma bonds. And so you can go back to this MO diagram here, right? And now you can think about, okay, if this is a pi bonding interaction, that's going to, again, it's the d orbital, how much is it raised in energy? That's going to raise this up, okay? If it's a pi accepting interaction, this is going to go down, okay? E pi is going to be negative, and this orbital is actually going to decrease in energy. So this is how we're going to quantify the strength of pi bonds and the strength of sigma bonds, and show how this corresponds to the overall energetics of transition metal complexes. Okay, and so what you end up getting is essentially a map. Okay, and this is one of the handouts that's on Web Campus, and I'll always give you this handout. I don't want you to memorize this by any means. I'll always give you this handout on the exam. And so what it's saying is, all right, here are your different metal atomic orbitals, the different d orbitals, and here is whether or not you have a sigma or a pi, and these are the different possible ligand positions. So you could think about, for example, an octahedral complex, you have 6 ligands in positions 1 through 6 here, okay? And so you can think about, okay, this is the Z. If I have a ligand in position 1, am I gonna have direct sigma bonding capabilities? And with the dz squared. Well, the dz squared, again, let me just draw this here. The dz squared looks like this, right? Shading not shown. And now you have a p orbital, let's say, or an s orbital. You have very direct interaction there. So it's actually it's as direct as possible. The angle's straight on, okay? Because it's as direct as possible, we give it a value of 1, saying it's worth 1 E sigma. Now, E sigma depends upon specifics of the ligand and how strong that intrinsic interaction is, but based on the angle, right, the angle's dead on, so we give it a value of 1. Now, with the dz squared here, you cannot have any sort of pi bonding interaction. And why is that? Well, again, let's draw the picture. And so you have your dz squared. Remember, we're just talking about dz squared here. And we're talking, so sigma has very good angular overlap. Pi has none. Why is that? Here's your dz squared. Look, the only way you can make a pi orbital, or try to make a pi orbital, is like this, right? And one of these is going to be shaded. Well, if one of these is shaded, let's say the node is dark, the donut is dark. Now you have half constructive interaction there between the two light shades, but equal amount of destructive, right, anti-bonding interaction. Overall, that gives you 0 bonding, so you can't have any pi bonding interaction there. So it's 0. And then you see these sort of, you know, strange intermediate cases, right, where let's see 1/4. Well, that's at position 2. That's at position 2. So that would be something like this, p orbital doing a sigma bond like that. Yeah, it's getting in a little bit to the donut, but it's also some destructive interaction between the light colored lobes. So, you know, it turns out to be a 4th. How do you figure out that's a 4th? That comes from the math of integrating the overlap of these two orbitals, okay? And we're not gonna do that. I'm just giving you the answer of all this integration. But it comes from just looking at, you know, how much can these orbitals, based on their shapes, overlap. All right, so you can only have, you know, a very weak sigma bond, sigma bonding interaction with a dz squared orbital if you're in the 2nd position here. And it turns out you can work through this, but you're not going to have any sort of pi bonding interaction at all, okay? And so anyway, this is for all the different types of geometry, common geometries. Here's setting you up for doing tetrahedral. Here can set you up for doing like a bent structure. And so here's going in more detail about the different structures that you can form. So like if you want to do trigonal planar, you'd use position 2, 7, and 8. That would give you a nice trigonal planar. You know, trigonal bipyramidal, you can do these different ones. Like we said, octahedral will be 1 through 6. If you want to just do square planar, you drop the axial ligands, just consider 2 through 5. Tetrahedron, you'd use 9 through 12, okay, etc. So what we'll do in the next video is we'll work through certain examples of using this angular overlap method.